Alright, I'm going to work through the Honors Math 2 Unit 4 review worksheet. And starting with number 1, can the following side lengths create a triangle, yes or no? Remember, to calculate this, you take the two smaller side lengths and add them together and see if it's bigger than the third side length. So on A, if I add the 7 and the 5, I get 12, which is bigger than 10, so I'm going to say yes on A. On B, in order to add the roots, I'm going to have to simplify them first. So square root of 75. 75 is 25, which is 5 times 5 times 3. So we end up with 5, square root of 25 times square root of 3, which is 5 root 3. Okay. Square root of 27. 27 is 3 times 3 times 3. So square root of 27 is the square root of 9 times the square root of 3, which is 3 square root 3. And the square root of 48 is, if you break that down, you get 4 2's and a 3. So you're going to end up getting square root of 16 times the square root of 3, which is 4 root 3. So if I take my two smaller values, add them together, I get 7 root 3, which is bigger than 5 root 3. So, yes. For fractions, I take my two smaller fractions. My smallest fraction is 1/5. And I add that with the second smallest fraction, 1/3. Got to get a common denominator, which would be 15. And I end up with 8 over 15. Sorry, 15, not 16. And 8 over 15, if I compare that to 1/2, well, here's 8 over 15. 1/2, if you get a common denominator, you get 16 over 30 here, and you get 15 over 30 on this one. So 8 over 15 is bigger than 1/2. So yes, it's going to work barely, but it works. On D, you add the 5 and the 10, you get 15, and it equals 15. So no, it's not going to work because the sum has to be bigger than the largest value. On E, I take a 1 and 12, that's bigger than a 12, so yes, that's fine. On F, 4 to the negative 2 power is going to be 1 over 4 squared, which is 16, 1 over 16. 4 to the 0 is 1. Okay, and then 2 to the negative 1 is 1 over 2. Okay, so we want to take our two smallest values, 1 over 16 and 1/2, add them together and see if that's bigger than 1. And you're not going to get that because 1/2 is going to be 8 over 16. Add that together, you get 9 over 16. This doesn't make 1, so this is not going to work. And then part G, I'm going to allow you guys to skip G just because you need a little more instruction on how to do fractional exponents before you do that. If you want to listen in, I could show you real quick, but I'm okay if you don't do this one. So 16 to the 1/2 means the square root of 16, which is 4. 16 to the 3/4 means the 4th root of 16 cubed, which is 2 cubed, which is 8. And then 125 to the 1/3 means the cube root of 125, which is 5. So if I add 4 and 5, I get more than 8, and so yes, that worked. On number 2, we're going to list the angles and sides in order from least to greatest. So the sides are going to be the easiest first, so I'll do that because those are given. And the smallest side is NM. Second smallest side is NO. Third smallest side is MO. For angles, the smallest angle is across from the smallest side. So the smallest side is 10, so the smallest angle would be angle O. The second smallest side is across from the second smallest angle, so angle M, and that leaves angle N to be the largest. The lengths of two sides of a triangle are 11 and 25. So what are the possible side lengths for the third side? Well, to find the lower bound, you subtract the 25 and 11. To find the upper bound, you add the 25 and 11. So you get all x values between 14 and 36. Use the given triangles to draw a segment showing the following. So if I want to show my altitude, I need to go through a vertex and I need to be perpendicular to the base. Base is just the side of the triangle. So that would be one possible altitude. You can draw two others as well, but that would be one possible. Angle bisector needs to go through a vertex and cut an angle in half. So to show that, I'm going to mark that this angle has been cut in half. Perpendicular bisector needs to bisect a segment in half, and it needs to be perpendicular to that segment. A median needs to go from a midpoint to a vertex. AE is the median of this triangle. So what does that mean? That means E is a midpoint, and so BE is congruent to EN. And so we're going to go definitely with part C. So that's true. AB congruent to AN, that could be true, but it could be false. So I'm going to write not enough info. Angle B congruent to angle N. Again, it could be true, but it may not be, so not enough info. And angle BAE congruent to NAE, not enough info. Which segment is the longest and which segment is the shortest? So I'm going to go after the longest first. The longest segment in triangle ABD is BD. The longest segment in triangle BDC is DC. Okay, so for the longest segment, I'm really debating between DB or DC, but since they're both are in triangle BDC, we can resolve that argument. We can and see that, well, in DBC the smallest side is DC. So DC, sorry, the longest is the longest side. Okay, so longest side is DC. For the smallest side, we're going to look for the smallest angles in each triangle.
Good morning, Clovis High School. What a great
So for the smallest in triangle ABD, smallest angle is 46, so AD is the smallest side in that triangle. In the other triangle, BDC, the smallest angle is 30 degrees. So now we're looking at, is BD going to be the smallest, or is AD the smallest? And so, since both are in triangle ABD, we can conclude that AD's got to be the smallest, because AD would be across from a smaller angle in that triangle than the other side, right? If you just look in ABD, AD is across from 46, but BD would be across from 70. So AD is the smallest side. All right, so in 10, what is intersecting in each triangle and what is the point of intersection called? So in triangle A, you could see that we have perpendicular bisectors. And perpendicular bisectors cross at the circumcenter. In triangle B, we see we have angle bisectors. And angle bisectors cross at the incenter. In triangle C, we see that we have medians. And medians cross at the centroid. In triangle D, we have altitudes. And altitudes cross at the orthocenter. All right, on to number 11. So here we're told, we're given that AD is perpendicular to AB. And so I'm going to mark that in here. So AD perpendicular to AB. And BC is perpendicular to CD. And BD is an angle bisector of angle ABC. So locate ABC, and that angle's cut in half. And so if I use the definition of angle bisector, that cut the angles in half. So I'd say angle ABD is congruent to angle CBD. Definition of perpendicular gives me right angles, so angle A and angle C are right angles. I can say that my right angles are congruent because all right angles are congruent. Step 2 is relying on step 1, because we could say we have, in step 1 we had an angle bisector, so I'm using the definition. Step 3 was relying on step 1, because step 1 told us we had perpendicular. Step 4 is relying on step 3, because that's where we found out we had right angles. And then I noticed in my diagram that we have a shared side, so BD congruent to BD, using the reflexive property of congruence. Six, we want to say that the triangles are congruent, ABD congruent to triangle CBD. We can see that by angle, angle, side, and that's relying on steps 2, 4, and 5, where I have my 3 congruent statements. And then lastly, I can say that AD is congruent to CD because corresponding parts of congruent triangles are congruent. Now for part B, we want to let AD be 5/7 x squared and CD be 2/3 x, and we know that those are congruent from 7, so that means the lengths AD and CD are equal. So I can set 5/7 x squared equal to 2/3 x. Set this equation equal to 0. Factor out a greatest common factor. Separate your factors so you can get 2 equations. X equals 0 is one of them, and so I found a value for x on that one. And then 5/7 x minus 2/3 equals 0. Keep solving that. I'm going to move it over here to get a little more space and add 2/3 to both sides. So I get 5/7x is 2/3. And I could divide both sides by 5/7 and make that work, or I can get rid of my fractions. And I'm going to get rid of my fractions, and what I do is I find a common denominator of 7 and 3 by multiplying them together, which is going to be 21. And I'm going to multiply both sides of my equation by 21. That allows me to get rid of my fractions, and here's how. So I'm going to get 21 times 5/7 x is equal to 2 times 21/3, and 21 divided by 7 is 3, so I get 3 times 5x, and 21/3 is 7 is equal to 2 times 7, so I get 15x is equal to 14, so x is 14/15. So I got another value for x. Now we want to use our x values to help us find AD. AD is 5/7 times x squared. Now if I plug in 0 into that, I get 5/7 times 0 squared, which is 0. And we can't have a side length that's 0. So that one's not going to work for us. So x equals 0 is what we call an extraneous solution, because when we plugged in 0, it gave us an answer, a side length equal to 0, and that's not feasible for this problem. So now I'm going to try the other x value. And so I'm going to rewrite this as 5/7 times 14/15 times another 14/15, because that's what it means to square. And we just have some numbers here, so lots of big numbers. So we got 5 times 14 times 14/7 times 15 times 15. And I'm going to try to reduce as much as I can before I multiply. So I'm going to divide by 7. Now 14 divided by 7 is 2. And I divide the 7 by 7. I'm going to divide the 5 by 5 and get a 1, and divide the 15 by 5 and get a 3. So now what's left on top is 2 times 14, which is 28. What's left on the bottom is 3 times 15, which is 45. And that's my answer. 28/45 units long is the length of AD. For number 12, we're given that AD is perpendicular to AB, and BC is perpendicular to CD. AD is congruent to CD. And we want to prove that BD is an angle bisector of angle ABC. Okay, so we have our givens. From the givens we got right angles. That's coming from the definition of perpendicular. I see in my diagram that I have a shared side, so I could say BD is congruent to itself because of the reflexive property of congruence. We can say the triangles are congruent by hypotenuse leg because in step 1, actually in step 2, we have right angles. In step 1, we have leg congruent to leg. And in step 3, we have hypotenuse congruent to hypotenuse. I want to show that BD is cutting angle ABC in half. In order to do that, I have to show that the two smaller angles are congruent. So I'm going to state that in 5, that angle ABD is congruent to angle CBD. And I can say that because they are corresponding parts of the congruent triangles in 4, which makes them congruent. And now because I have that in 5, I can say, hey, that's enough support to say it's obvious that it is an angle bisector using the definition of angle bisector. Now in part B here, we want to let angle ABD be congruent to angle CBD. That's what we proved in the in this problem. So that means that 35x squared plus 10x is going to be equal to x plus 2. And we can solve for x. I'm going to set the equation equal to 0 by subtracting x from both sides, subtracting 2 from both sides. When you do this, make sure before you factor that your terms are ordered from highest power to lowest power. This is a trinomial, so I'm going to try trinomial factoring. What two terms multiply to 35x? Sorry, I need to multiply that with -2, don't I? Let's do that. So I'm multiplying the 35x squared and the -2. That gives me -70x squared and 9x here. So I'm looking for two terms that multiply to -70. Alright, so 70 is 7 times 10. 10 is 5 times 2. And we want this to add up to 9. So 7 times 2 is 14. So 14 and 5. So what if I do that? 14x minus 5x. That multiplies to -70 and adds to 9. So now I split the middle. The 9x to 14x minus 5x. Factor by grouping. I'm going to factor out a 7x from the first two terms and get 5x plus 2 remaining, minus factor out a -5, actually sorry, a -1. I'm left with 5x plus 2. Sorry, let me clean that up a little bit so it looks better. And we notice that both of these terms have a common factor of 5x plus 2. So factor that out, and we're left with a 7x minus 1. Separate those factors, 5x plus 2, set that equal to 0, and 7x minus 1, and solve. And we get x is -2/5, and x is +1/7. And we want to use these x values to help us find the measure of angle CBD. So the measure of angle CBD is given from the formula x plus 2. So if I take x, if I let x be negative 2/5, I'm going to get negative 2/5 plus 2, get a common denominator, and I end up with 8/5. So that's one possible answer. I also have another x value of 1/7, so I'm going to plug that in. So the measure of angle CBD is x plus 2, and when x is 1/7, we get 1/7 plus 2, which is 1/7 plus 14/7. I'm changing 2 to a number with a fraction with a common denominator, so we end up with 15/7. And both of these are representing degrees, right? Because we're finding the measure of an angle. So 8/5 degree and 15/7 degree. Very small degrees, right? All right. Number 13. We're given that UT is the perpendicular bisector of LD. Reason given. And it wants us to prove that LT is congruent to TD. Okay. So here's in blue my perpendicular bisector, because a perpendicular bisector always bisects a segment. It's bisecting LD right here, which means it's cutting that segment in half. It's perpendicular, meaning they form a right angle. If you have that, then you can use the perpendicular bisector theorem that says that these two sides will be congruent, and we end up with this larger isosceles triangle. And so that is exactly what's happening here in number 2. LT is congruent to TD by the perpendicular bisector theorem. So you want to know that theorem. Alright, so 13 is asking us to find x, LT, and DT. Now, if I find LT, I find DT because they're congruent, right? So I know that LT is congruent to DT, and so I'm going to set 25x to the third equal to 8 minus 2x to the third. And then I want to make this equal to 0, so I'm going to add 2x to the third and get 27x to the third. Subtract 8. This is the difference of two perfect cubes, which is going to factor to 2 terms times 3 terms. And I know it's a perfect cube because 27 is 3x times 3x times 3x. So I'm going to put 3x here. 8 is 2 times 2 times 2, so I'm going to put a 2 here. Right? That's how I get my 2-term factor. To generate my 3-term factor, I take the 3x times 3x and get 9x squared. And then for the middle term, 3x times 2, which is 6x, and then 2 times 2, which is 4. And then I use the SOAP to help me remember what sign. The original problem had a minus sign between the cubes, so I use the same sign here, the opposite sign here, and this one's always positive. Now when we're solving, remember that the trinomial that's given when you factor a difference or a sum of two cubes is not factorable. And so at this point I'm not going to ask you to solve that if it's not factorable. But the 3x minus 2, we could set that equal to 0 and solve and get x is 2/3. So we found x, that was one of our jobs, and then now we want to find LT. So LT is 25 x to the third power. And x is 2/3, so it's going to be 25 times 2/3 to the third power. So that means 25 times 2/3 times 2/3 times 2/3. And we can think of that as 25 over 1. And we just, when you multiply fractions, you multiply all the top with the top, or the numerators together, and you multiply the denominators, the bottom with the bottom. So let's see here. We got 25 times 2 is 50, times 2 is 100, times 2 again is 200. And then 3 times 3 times 3 times 1 is 27. And that is our distance, 200 over 27 units for LT. That is also the same as DT, so LT and DT, because we proved that DT and LT were congruent using that perpendicular bisector theorem. Alright, number 14. D is given as the circumcenter of ABC. What that means is that 3 perpendicular bisectors were drawn and they crossed at point D. So in this proof we got our given, and we want to show that AD is congruent to BD. So what I'm going to do here is I'm going to say that, sorry, I'm trying to open this up here. It's giving me a little trouble. There we go. I'm going to say that ED is a perpendicular bisector of AB. And I know that because D is the circumcenter, and the circumcenter is created by perpendicular bisectors. We can also see that it's drawn in here, right? So that's what I'm going to write in 2, so that ED is a perpendicular bisector of AB. And that came strictly out of the definition of circumcenter in this problem. We can also add to that there's 2 other perpendicular bisectors, but we don't need them. So now I want to show that AD is congruent to BD, and we have a perpendicular bisector. And remember that in the last problem, when we had a perpendicular bisector, the perpendicular bisector theorem says that these 2 sides that form that an isosceles triangle will be congruent. And that's exactly what I want to prove here. And so I am going to use the perpendicular bisector theorem again. And we're done with our proof. I want to find x. I know that AD and BD are congruent now because I proved that. So I'm going to set x cubed plus 2x squared plus equal to x plus 2, right? Because those are the 2 side lengths here. And set this equal to 0. And factor by grouping. So I'm going to factor an x squared out of the first 2 terms, and a -1 out of the last 2 terms. And I get x plus 2 times x squared minus 1 is 0. I can factor one more time. That x squared minus 1 is a difference of 2 perfect squares. So x plus 1 times x minus 1 equals 0. and I get three factors: x plus 2, x plus 1, x minus 1, and I get three answers for x: negative 2, negative 1, and positive 1. So I found three different possibilities for x. Now I want to find the distance from A to D. And AD is given as x plus 2. So if I plug in a negative 2 into that, I get negative 2 plus 2, which is 0. And so that didn't make sense for that side length. So that's an extraneous solution. We're not going to do that one. Alright, so let's try plugging in x equals negative 1 into x plus 2. And we get negative 1 plus 2, which is a distance of 1. So that can make sense, yep. And then let's try x equals 1 into AD. And we get 1 plus 2, which is 3. So we have two possible answers. It could be 1 unit long, or it can be 3 units long. And we were asked to find BD as well, and we proved that AD and BD are congruent, so we don't need to solve for BD. We could just say, hey, this is also equal to BD, and this one's also equal to BD. So we have our two possible answers for BD and our two possible answers for x. Alright, number 15. Given that E is the orthocenter and the incenter, prove that AF is a median of ABC. Alright, so if E is the orthocenter, that means that it's a segment that altitudes go through. Okay, and an altitude gives you perpendicular. So in our picture, we see that AF is going through E, and so I know that AF is an altitude of the triangle, and that's coming straight out of the definition of orthocenter. From that, I can say, well, an altitude gives, perpendicular. That's the definition of an altitude, right? And so I can say that AF is perpendicular to BC by definition of altitude. And then from perpendicular, I could say that angles CFA and BFA are right angles by definition of what it means to be perpendicular. Now the incenter, if E is an incenter, that means that AF would be an angle bisector. Of BAC. And if that's an angle bisector, then angle BAF and CAF are going to be congruent. And that's coming out of the definition of an angle bisector. we see from our picture that AF is a shared side of the two triangles, so I'm going to write AF is congruent to AF by the reflexive property of congruence. And now we have that the two triangles are congruent by angle side angle. And this is relying on steps well, let's see here. Looks like we're missing a step still, because I need 3 congruent statements. I have 7. I have 6. But I need a step saying that my right angles are congruent to each other. So I think this might be a little mistake on my end. I need probably something between 4 and 5, and I'm going to write it out here. So let's say step 4.5. Something saying that angle BFA is congruent to angle CFA. And my reason would be all right angles are congruent. So that is a needed step that we don't have in here. But we'll just put it right there, okay? So now I can say that these triangles are congruent through step 4.5, 6, and 7. Okay, I'm trying to show that AF is a median, and so in order to do that, I have to establish that BF is congruent to CF, and I got that by corresponding parts of congruent triangles being congruent from step 8. And now I can say it's median by definition of median. Okay. Number 16. Given that AC passes through the incenter of BCD and through the incenter of ABD, prove that AC is perpendicular to BD. First thing, notice it's proving 2 segments are perpendicular. So I know I'm going to be using the converse of the perpendicular bisector theorem. And perpendicular bisector theorem is going to need two prerequisites. One, that we have segments that form a isosceles triangle, and 2, that we have segments that form a bisected base. And so we're going to look for that as we go through here. From the definition of incenter, so if AC passes through the incenter, that means that AC is an angle bisector. Well, in BCD, it would be angle BCD. So I'll mark that in there. And because it also goes through ABD, it's going to be angle BAD, the bad angle. All right. And so in 3, I could say that angle BAE is congruent to angle DAE, and angle BCE is congruent to angle DCE. By definition of angle bisector. 4 is saying that our triangles are congruent. So triangle ACD is congruent to triangle ACB. So in order to establish this, it looks like we're going to have to add in another step that I forgot again to place in here, and that's the shared side between the two triangles. And so we're going to make a step 3.5 that AC is congruent to AC. And the reason is going to be the reflexive property of congruence. And so now I can say these triangles are congruent by angle side angle using steps 3 and 3.5. So if I want to use the converse of the perpendicular bisector theorem, I need those two prerequisites, right? And so in 5 you see AB congruent to AD. AB congruent to AD. Okay, and so you see this triangle here, ADB, is looking at like an isosceles triangle now, right? Because we showed that AB and AD are congruent. And then BE so I'm realizing that there's a couple other things that are missing in here, because we can get AB's congruent to AD, and we're going to keep that. But we can't get BE congruent to DE because those are not parts of the congruent triangles. We want to get that, but we can't put that there yet. So I'm going to put CPCTC here. And I'm going to, this is relying on step 4. And we need to still build up to BE congruent to DE. And we'll do that, but we're going to have to add a couple steps in between 5 and 6. So step 5.1 is going to now be that AE is congruent to AE. And my reason would be reflexive property of congruence. So now I got that, and now I can say that 5.2, that triangle BAE is congruent to triangle DAE. And my reason would be side angle side. The steps that I'm relying on are going to be, let's see, side angle side. We have the angle came from 3. One of the sides came from 5, and then the other one came from 5.1. And then we can make our 5.3 be what we wanted. That BE is congruent to DE. That's our bisected base. Oops, I was going to write bisected base. This is coming from CPCTC, because they're corresponding parts of the congruent triangles in 5.2. Alright, so those were needed before I get to 6. So now I have what I needed in 6. So 6, I can now say that the perpendicular by the converse of the perpendicular bisector theorem, and those were relying on the 2 key steps, one in step 5 and one in step 5.3. So, so between 3 and 4, we had this one, 3.5, and right after 5, between 5 and 6, we had to establish 3 more steps. Alright, so I need to edit this worksheet. That was 16. 17. The coordinates of the vertices of a triangle are given. Alright, so find the coordinates of D, which are the midpoint of AC. So if D is the midpoint of AC, then I take my x value in A plus my x value in C over 2, comma, y value in A plus the y value in C over 2, and simplify this. And we get point D is 2, 2. And we need the coordinates of E, which is the midpoint of CB. So CB, so the x value of C plus the x value of B over 2, the y value of C plus the y value of B over 2. 7 plus 4 is 11. 2 plus negative 5 is negative 3. So we get 11 over 2 and negative 3 over 2. So mathematically show that DE is parallel to AB. So to do that, we need to find the slopes of each. So let's find the slope first of AB. So the slope of AB, the formula is going to use the y value of A minus the y value of B over the x value of A minus the x value of B. So 2 plus 5 is 7, and then this is negative 7. So we end up with a negative 1 for our slope for AB. The slope of DE, if they're parallel, then they're going to have the same slope, so I should get a negative 1 again. So I'm going to check here. So the y value of D minus the y value of E Alright, before I move on any further, I'm going to draw what we have here. So we have A, B, C, and D is the midpoint of AC. And E is the midpoint of CB. And we're trying to show that the slope of AB is parallel to the slope of DE. Okay, so back to the slope of DE. So 2 minus negative 3 over 2. And then now the x value of D is going to be 2 minus the x value of E is 11 over 2. And I'm not seeing that this is going to be negative 1, but let's see here. So 2, I'm going to change to 4 over 2, get a common denominator, plus 3 over 2, over, and then 2 here, I'm going to make 4 over 2 minus 11 over 2. And then add these fractions. I get 7 over 2 divided by 11. So 4 minus 11. Here we are. We're going to get our negative 7. So maybe this is going to work out here. And we got a positive 7 over 2 over negative 7 over 2. That does give you negative 1. So we do have the same slope. And so since the slopes are equal, we can say that AB is in fact parallel to DE. Then part C says find the slope of the altitude of ABC to base BC. Well, the slope of BC, I'm going to find that first. And so the slope of BC, using the slope formula, you take your y value of B minus your y value of C over your x value of B minus your x value of C. And you get negative 7 over negative 3, so 7/3. And the altitude is perpendicular to this base. So the slope of this altitude is going to be the opposite reciprocal of the slope of BC, which is negative 3/7. And then D says mathematically show that the length of DE is half the length of AB. All right. So let's find the length of AB first. And so I'm going to plug in some values. So AB, so the x value is negative 3, and we got 4. So negative 3 minus 4 squared plus 2 minus negative 5 squared. Square root of that. Let's plug in the distance formula and just work through this. So negative 7 squared plus 7 squared. And so that's going to be 49 plus 49, which is 98. So square root of 98, and that is 49 times 2, and 7 times 7. So we get square root of 49 times the square root of 2, which is 7 root 2. So that's AB. And we want to show that DE is half that length. Okay. So the x value for D is 2 minus the x value for E squared plus 2 minus negative 3/2 squared, square root of that. We got some fractions. It's going to make it a little more difficult, but we'll make it through. So get a common denominator. And I shouldn't do 4 over 4. It should be 4 over 2 on both of these. And then from there we get negative 7 over 2 squared plus 7 over 2 squared, square root of that. And we're going to end up with 49 over 4 plus another 49 over 4, which is 98 over 4. And this is the same thing as splitting it up, square root of 98 over the square root of 4. And that's the same thing as the square root of 98 over 2, which is the same thing as a half of the square root of 98. And we already found back here that the square root of 98 is 7 root 2. So we could say that this is a half of 7 root 2. And by the way, remember, AB was 7 root 2, so this is a half of AB. So we just showed that DE is half of AB, and that's what we wanted to show. And that's it for our review.